Welcome to AP Chemistry. In this video, we will introduce the concept of enthalpy and relate it to the three types of intramolecular bonding that we have begun to discuss. Localized covalent bonding, mostly in nonmetals, delocalized covalent bonding, mostly in metals, and ionic bonding between cations and anions. We begin with a review of the concept of internal energy, symbolized by U. Recall that U stands for the entire amount of both potential and kinetic energy in our chemical system. That is, all of the attractions between positive and negative electric charges that serve to decrease potential energy, as well as all of the repulsions between positive and between negative and negative electric charges, as well as all of the kinetic energy, translational, rotational, vibrational, in the movements of the particles that make up our system. Now, any change that will occur in the internal energy of our system will come in either of two forms: heat, symbolized by Q, or work, symbolized by W. Both of these are examples of kinetic energy that can flow into or out of our chemical system. Heat here should be thought of as kinetic energy due to the random movements of the particles, whereas work is kinetic energy due to an overall movement of the particles in a certain direction. Now, a bit later in the course, we will derive this work equation specifically for gases under constant pressure. The W equals negative P times change in V. We will only deal with work of a constant pressure change in volume nature. That is, the compression of gases or expansion of gases under constant pressure. However, it will be a couple of units before we get to this type of gaseous work. Right now, our focus is heat, specifically the heat change possible within our chemical system. Rearranging the equation provided to solve for Q, we get a definition of enthalpy, symbolized by change in H. Enthalpy is defined as the heat energy change per chemical process that has occurred. Enthalpy is distinctly important for us in chemistry because that certain amount of heat energy change occurring per unit process specifically comes from the difference in potential energies in the chemical bonds that make up our system. The difference between the potential energy of the products and the potential energy of the reactants. This is an incredibly important point because enthalpy change is like an indirect way for us to view what is actually going on in the attractions and repulsions within our chemical system. We have already discussed that any process that is purely bond breaking will require an absorption of kinetic energy, and that any process that is purely bond forming will require a release of kinetic energy. Yet it is extremely rare for a chemical process to be a pure form of just either of these. Most chemical reactions will be a various mix of bond breaking and bond forming. When, however, there is more kinetic energy coming into our system to break bonds than kinetic energy flowing out of our system to form new bonds, we call this type of reaction endothermic. Endo meaning in, and therm literally heat. The change in enthalpy in the system for such a process would be positive. When there is less kinetic energy coming into our system to break bonds than kinetic energy flowing out of our system to form new bonds, we call this type of reaction exothermic. Exo meaning out, and therm again for heat. The enthalpy change in the system for such a process here would be negative. Now, enthalpy is described as a state function. That is, enthalpy does not depend upon the path by which the chemical process occurs. It simply describes the state of our system. The practical significance of this is that the enthalpy change associated with a certain chemical process, represented by a chemical equation, functions as part of that equation and is dependent upon the specific coefficients. That is, the enthalpy change associated with a specific chemical process is algebraic and functions like the components of any typical algebraic equation. To take a specific example, it does not matter if we complete a chemical process in 2 steps or in one. If we calculate the overall change in enthalpy for both, the change will be exactly the same. In order to estimate the enthalpy change for a chemical process with molecular compounds, we will be using a table of bond energies. In order to calculate the enthalpy change for a chemical process, you should first draw their Lewis structures for both reactants and products, and then create a table of all of the bonds being broken on the reactant side, and another table for all the bonds being formed on the product side. Then, using the bond energies, you should multiply each number accordingly, understanding that all bonds being broken will have a positive value for their bond energy, and all bonds being formed will have a negative value for their bond energy. When both are tabulated, Their sum will be the total enthalpy change for the chemical process. Now, even more important than the simple calculation of enthalpy changes is understanding the significance of what makes bond energies different from each other. Here, we return to Coulomb's law of electrostatic force. The strength of electrostatic force is directly dependent upon the strength of attractive charges and inversely dependent upon the distance between them. Take, for instance, the HF bond versus HCl and HBr and HI. Note that the size of these bonds will increase due to the atomic size of fluorine, chlorine, bromine, iodine increasing as we go down that group. Furthermore, the difference in electronegativities is much larger in reference to hydrogen and fluorine than in reference to hydrogen and iodine. Therefore, bond energies will go substantially down that set. However, note how these compare to the bond between hydrogen and hydrogen. Why is this still so significant? It is because hydrogen exists in the 1s sublevel, and this bond length will be significantly smaller compared with the others. Therefore, its bond energy is noteworthy. We will now discuss calculating change in H for other bond types in the next part of the video. Provided is a table of the types of intramolecular bonds that we have been referencing. To estimate enthalpy change for localized covalent bonding, we have just used bond energies, which also function as a relative comparison of the strengths of those bonds. For delocalized covalent bonding, as in the case of metals, we will simply use their sublimation energy, that is, the energy required to go from the solid to gaseous state, in order to compare their relative strengths of metals. This will primarily be done in class. For the rest of this video, we will take the case of calculating the enthalpy change for the formation of certain ionic compounds. This type of calculation will actually be noteworthy in that we will integrate both the use of sublimation energies for metals and bond energies for nonmetals, as well as previously used energies such as ionization energy and electron affinity, in order to calculate a total change in enthalpy for the formation of an ionic compound. Now, ionic compounds are bonded extremely well together. This is first due to the extreme difference in electronegativities between the atoms bonded to each other. The much weaker electronegative particle loses its hold on its valence electrons, and the much stronger electronegative particle attracts and gains these into its orbitals. This results in an alternating formal charge among positively charged cations, cat meaning down, as electrons are torn down and away, and negatively charged anions, an meaning up, as electrons being built upon. This is significantly different from molecular compounds, in that there is essentially no beginning or end to the attractions that exist within a solid sample of an ionic compound. The ionic bonding is literally pervasive in repeating lattice formation throughout the structure. In order to break the attractions within the ionic lattice, one would have to vaporize the entire salt, converting them into the gaseous state, which would require an incredible amount of energy. Thus, it is their continuing, repeating lattice arrangement of alternating charges which give ionic compounds their incredible bonding strength. In these simulations, 1 second is equivalent to 1 picosecond, or 1 times 10 to the negative 12th second. Also, note how the ions self-organize, finding the right equilibrium between maximizing attractions and minimizing repulsions. Take, for example, an absurd system in which there are 26 sodium ions. Notice how they would behave in relation to each other. If we were to add, say, 6 helium particles to this system, notice the effect, if any, which would take place. However, now notice the radical difference in adding 6 chloride ions. And finally, when we add an equal number of sodium ions to chloride ions. This is why ionic compounds have somewhat of a different type of formula than molecular compounds. That is, ionic compound formulas are always in the reduced form of their whole number ratios. Observe, though, how the crystal arrangement changes when the ratio of charges is not simply 1 to 1, as in the case of sodium sulfide. But the differences in charge is not the only aspect that will contribute to greater attractions. The size of individual cations and anions will radically affect attractions as well, again according to Coulomb's law. With this information in mind, we will now discuss the process necessary to calculate the enthalpy change for the formation of an ionic compound from its elements in their naturally occurring state. We begin our example with solid sodium metal and molecular fluorine gas. The first movement necessary is to sublimate the sodium metal so that sodium might exist in the gaseous state. This value is a positive 109 kilojoules per mole. The second movement is to ionize the sodium atom in order to lose the only valence electron it has, its first ionization energy, costing a positive 495 kilojoules per mole. Third, we break half a mole of F2 gas in order to make 1 mole of atomized fluorine, another positive 77 kilojoules per mole. Notice that up to this point, all the movements have been endothermic. The fourth movement is to add an electron to the fluorine atom, its electron affinity, which results in a change of negative 328 kilojoules per mole. However, if we stop here, all we have is still an overall endothermic process. Yet, if you look up any demo for the formation of a salt, you will always observe a fiery display of a highly exothermic reaction. So, what is missing from our calculation? The key is that we have not yet actually made the salt. We have only made gaseous sodium ions and gaseous fluoride ions. However, as we have already discussed, this is not where the attractive forces in an ionic compound lie. Rather, when those ions are brought together in lattice formation, an incredibly strong attraction will occur, and copious amounts of energy will be released. We call this energy specifically lattice energy, and it is this energy which drives the exothermicity in the formation of a salt. Only with this can we then calculate the total enthalpy change correctly for the formation of an ionic compound. Try pausing the video and adding these components together in order to calculate the enthalpy change for the formation of magnesium oxide. Note how lithium fluoride's lattice energy was negative 1047 kilojoules per mole, whereas the magnesium oxide's lattice energy was negative 3916 kilojoules per mole. They differ by an approximate factor of 4. Can you decipher where the source of this difference lies? Furthermore, if we compare lithium fluoride's lattice energy at negative 1047 kilojoules per mole to sodium fluoride's lattice energy at negative 923 kilojoules per mole, we see another component that affects differences in lattice energies as well. Both of these components are found in the lattice energy equation provided above, which looks extremely similar in form to Coulomb's law. Again, it is the magnitude of charge and the distance between the particles that will affect their bonding strength. From this sense, we are now able to begin to compare chemical properties between substances due to the relative strength of their chemical bonds.